this is review video 41. What is equilibrium? Equilibrium is a state that a reversible reaction can attain over time. It's not a reaction itself, but rather a state of being that some reactions can get into. So the only reactions that can fall into a state of equilibrium are reversible reactions. And reversible reactions are types of reactions that can go forward and backwards simultaneously. And so they're different than normal reactions because typically normal reactions are written out like this: A plus B yields AB. And so we have a one directional arrow indicating that the reaction is going to go forward. All of our A's and all of our B's are going to react together to produce that compound. But with a reversible reaction, we don't necessarily only get the forward reaction. When you mix A and B together, yes, initially you will be going forward to produce AB as a product. However, as you accumulate AB, they're going to start crashing into each other and actually break back apart so that we can start moving backwards over time. And eventually, once this starts happening over and over and over again, we can kind of settle into a state of equilibrium where our rate of our forward reaction and our rate of our reverse reaction will start to equal one another, and we kind of just settle down. All right? Not every type of reaction can be reversed. It kind of depends on what's going on. So reversible reactions tend to have products and reactants with similar stability. And by stability, I can mean quite a few things. So you can think of stability as their level of entropy or enthalpy, or like any number of things can control how stable a reactant or product is. But realize that for reactions to go in both directions, our reactants and our products have to be similarly stable. Not exactly the same, but similarly. In addition, our activation energy for our forward and our reverse reactions will usually be similar as well. Because if it takes way more energy to go backwards than it does to go forward, then it doesn't make sense for that reaction to be easily reversible. But the way you pick out a reversible reaction right off the bat is by looking for this double-pronged arrow. Because again, like I said before, typically we've only used the single-prong arrow pointing to the right. But when you start seeing this one, it indicates that the reaction can be reversible. So thinking about both the state of equilibrium and reversible reactions, we can kind of start to parse together if a reaction is at equilibrium or not. So we know a reversible reaction has reached a state of equilibrium when your rate of product formation equals your rate of reactant disappearance. So looking at this graph over here, we can see that this graph is telling us concentration of our reactants and products over time. So up here we have line A and line B. Those are our two reactant lines, and I know that because we tend to start out with reactants, right? So their concentrations are going to start pretty high, and they get somewhat lower over time, right? We can see that negative slope here. Whereas our product, initially, before I mix my reactants together, I don't have any products, so they tend to start low, and then they're going to increase over time. But what you're seeing right about here is that our levels of our reactants and our products have started to level off or equalize. That doesn't mean that you have the exact same concentration of reactants and products, because you can see that those three lines are at three different concentrations, but rather over time, those concentrations are no longer changing. So they've reached that state of equilibrium right about there when those lines level off. And just because there's several ways to say the same thing, when our rate of product formation equals our rate of reactant disappearance, when we're in equilibrium, we say that the rate of the forward reaction equals the rate of the reverse reaction. So those two statements mean the same thing. And again, please note, just because the rates are equal, that does not mean that the concentrations are equal. It just means that we are producing product at the same rate we are producing reactant. It doesn't mean that we have the same amount of product and the same amount of reactant. You'll see that next week when we start our equilibrium unit. So we already looked at this graph, so I'm not going to look at that one too much again, but I just wanted to show you a couple of other equilibrium graphs and what they can look like. So with this one over here on the left, we again see that our reactants are starting high and our products are starting low. But in this case, our equilibrium, we actually end up with more product than we have reactant when we reach equilibrium. So again, this is indicating that our rates have stabilized, but we have different amounts of product and reactant at any given time. And then in this graph over here, we have reactant starting high, product starting low again. However, we end up with more reactant than product when we reach equilibrium. And again, both are considered equilibrium because our rates are not changing anymore. That line has leveled off, but again, we have different amounts of both. If you have any questions about that, please feel free to ask me.